I can find where the center of mass for me is. Usually for us human, the center of mass is our stomach. That's where the center of mass is. It's amazing how our body knows that. When you go to stand up, you always lean forward such that your stomach sits under your feet. So when you stand up, center of mass directly below that. But if you don't believe that, you want to calculate what the center of mass is, one easy way to do it, you can take a beam. We'll take a beam actually. And let's say the beam is uniform. It's made out of the same material, 2 meters long. It has a mass, I don't know, of 10 kilogram. It's plywood, piece of plywood. And you have somebody lay on top of it. It's going to be a long person. Here we go. That's the person laying on that beam. Let's say the person happens to be 2 meters long too, just for simplicity. The person is 2 meters long. And the mass of the person, so nothing is hanging, the mass of the person is, 75 kilogram. And you want to find the center of mass. All you got to do, get 2 scales, go to the gym, lay the person on that, get 2 scale, put one on this end, and read what the scale is saying. And read what that scale is saying. One on each end of it. We read the numbers on the scales. I'll just throw some numbers here. This is 375. It reads 375 Newton. And this scale reads 458. Notice the one where your head is actually has a larger value because the center of mass for the person is closer to your head than to your feet. It's your stomach. Your stomach's closer to your head than to your feet. And if the person's just laying there and you just look at the numbers, you can calculate where the center of mass for the person is. We have no idea. You want to measure it from his feet or his head? It's up to you. From where? You decide. Head? Okay. Let's call that distance, that's the 0 mark. And let's call this distance here x for center of mass for the person. XCM, center of mass. I want to know where that distance is. So we're going to treat that person as a weight straight down here, where the center of mass is, and the weight is going to be 75 times the 9.8. Which is 735. So the weight of the person is going to be 735 Newton, and it's some distance xcm from the head. We have no idea what the value is. The board itself has a weight of 98 Newton, right? 10 times 9.8, that's 98 Newton. And the board itself is uniform, so the center of mass for the board is going to be where? The 1 meter? Because the whole board is 2 meters long. Since nothing is spinning, we have static equilibrium. So you will find that if you take all the forces in the y direction pointing upward should equal all the forces pointing down. There is nothing in the x direction here. Let's see if that's true. Add them. If I did the prompt correctly, pointing upward 375 plus what? 458. Pointing down is what? The 98 plus the 735. I could have made the problem more fun actually, not to tell you what the weight of the person is. So you get to figure out what the weight of the person is, because if you put mass times gravity, you can calculate the mass, the weight, and the mass of the person. Does that equal to each other, these two numbers, when you add them? Could be rounding error. The right side is 833. The left side is what? 375 plus 458? 833. Good. So I didn't screw things up. Again, I could have made the problem more fun and said, we don't know how much, what's the mass of the person. Can you tell me what the mass of them? Instead of putting 735, we go m times g here. We know what g, which is 9.8. Can you find what m is? So I could have solved it for m. I'm not interested. My focus was on the center of mass. How can I find the center of mass? We do the torque. Sum of the torque is 0. And you pick any point on that beam and you calculate the torque. I'll use that point because we mark that as the 0 mark, so since everything measured from that point, it makes my life easy. This force has 0 torque because it goes through the pivot point. We get the person. The person actually, notice if that's the pivot, is going to make the board spin this way. And isn't that counterclockwise? That's a positive torque. And what's the value? 735 times x center of mass. The 98 is going to make it spin counterclockwise. 98 times 1. The distance from here is 1 to that pivot point. This scale here is pushing upward. That's clockwise. That's a negative 375. And the distance from this scale to that pivot point is actually 2. That's times here, not x here, in case you're wondering. So 735 x center of mass equals 375 times 2 minus 98. I'm combining, moving to the right side, no in one step. 652. Can we get the center of mass? 0.887 or 89 meters. So notice closer to your head than to your feet. It's 8.9 or 0.9 meters roughly this way. It's 1.1 meter from his feet. So we're going to do the center of mass by just calculating this here, or using these two equations. If I have a scale, and on the scale I have the beam that looks like this. On this end I have a mass attached to it. We'll call it M2. They're not the same mass. On this end we get a mass attached to it called M1. And we try to find where the center of mass is. You can actually move your finger till it's balanced here. So now it's balanced. If you hold it with your finger, that means your finger is pushing upward there. And the system is balanced. Let's call the distance from here to there x1. Let's call the distance from here to there x sub 2. How do we find the center of mass? Where is it going to be? Got to shut it off. Now, let's see. Sum of the forces pointing upward should equal sum of the forces pointing down. Well, that your finger or the string, whatever is holding that, is going to balance what? The weight of these two. Plus the mass of the beam, whatever that beam is. So when you look at the beam here itself, Oh, well, not in the middle here. I don't want to put in the middle. Well, the beam itself has a mass, which has a weight now. The weight of the beam is the mass of the beam times 9.8. You got the weight here. We'll call it weight 2, which is M2, mass 2 times 9.8. We got weight 1 here, which is mass 1 times 9.8. And we got your finger or the string, whatever is holding that here, F, whatever, for a finger, holding it. You're holding the scale like this in your hand. And this is x of 1, and this is x of 2. Just like before, center of mass. First we do all the forces pointing upward equals all the forces down. Upward we have F, down we have what? M1 times 9.8, M2 times 9.8, and the mass of the beam times 9.8. We can figure what F is, what that force is, if we know where you hung there and how much the beam weighs. If you want to make life easy, assume the beam has no mass. If the beam has no mass, this piece will disappear. So that force will equal to this weight and that weight. I'm just leaving in general there. Sum of the torque is 0. So the torque is going to be what? Pick a point, and I'm going to pick where my finger is to calculate the torque. That point right there. Let's pick that point. So the torque by this force is 0. Or I could have picked that point, you know. Doesn't really matter what point I use there. It's up to you, whatever point you want to use. Sum of the torque is 0. Because once you know what x1, you know where the center of mass is, right? If you know what x1 or x2, if you know what these are, you know where the center of mass. Let's assume the beam has a length of, I don't know, 1 meter. Because otherwise you get too many unknowns. Let's see what that means. So let's begin with this one. This one's going to make it spin which way? Counterclockwise? So that's going to be what? Positive torque, which is mass 1 times 9.8 times that distance, which is x of 1. What about these two here? They're going to make it spin which way? Clockwise. That's a negative. Mass of the beam times 9.8 times the distance from here to there. What's that distance from here to here? From here to there. Okay, let me rephrase the question. What's the distance from here to there? 0.5. Subtract from it this distance, which is what? So it's this distance minus that, isn't it? So it's really 0.5 minus x of 1. Because the beam is 1 meter, this is halfway through. That's 0.5. I want the distance from here to there, not to this point, to this one. So it's 0.5 minus x of 1, because that's x of 1. And what about that piece? It's going to have a torque of what? Negative mass 2 times 9.8. And what's the distance from here to there? I can write x2, but if I write x2, how many unknowns do I have now? 2 unknowns in that equation. I can't solve it. But can I write x2 in terms of x sub 1? What is that distance from here to there? It's 1 minus x1, right? I can write x2 for now. Let's leave it as x2. Leave it as x sub 2. That's fine for now. What do you notice about this equation? You have the 9.8 showing up in every one of them, right? So you can drop that out because it shows up in every one of them. Mass 1 times x1 minus mass of the beam times 0.5 minus x sub 1 minus m2 times x sub 2. Again, if I take x sub 2 and replace it with what? 1 minus x sub 1, how many unknowns do I have? Only one unknown. I'm assuming I know these masses. So if I replace x sub 2 1 minus x sub 1, and now what you see, I only have how many unknowns? One unknown, x sub 1. We know the mass of this, we know the mass of this, we know the mass of the beam. I just didn't give them to you. But we normally know these things. And I should be able to solve it for x sub 1 where the center of mass is going to be. Solve for x sub 1. We can find the center of mass for any object, you know, and that's your center of mass. The book didn't want you to go through the math and kill yourself, and says, you know what, instead of deriving all the stuff here, you can do the math. And in this example, actually, I'm going to show you, they neglected the mass of the beam. It says ignore the mass of the beam. It's not worth adding. If you neglect that, if you make that a 0, what will happen? This will disappear, and you end up with that one. So they're saying to find the center of mass for an object like this, if you neglect the mass of the beam, if you have two weights hanging, center of mass is mass 1 times x1 negative plus mass 2 times x sub 2 over the sum of them, sum of the two masses. That's the equation they use. That's what just going through what we did there on a longer scale. I mean a shorter scale. We did it with a long way. So you take the mass of the first one. Obviously one has to be minus, one has to be positive, because one makes it spin clockwise, one makes it spin what? Counterclockwise. That's why one is negative x sub 1, one is positive, because that will make it negative torque and positive torque, you know, divided by the sum of the two masses. And if you got more than 2, they'll do the same thing. So notice we have all these pictures. We're going to show where the center of mass is. You got to find out where each piece is in relation to that, to the center of mass. Compare mass. Okay, so that's really the only thing I want to talk about, the center of mass. Nothing really outrageous or fancy there. The next section is the big one, is the application of torque, dynamic application of it. And we're going to talk about it. Conservation of angular momentum, rotational work and power. God, we still have a lot of sections here. That's a small chapter. Let's take a break.